Sorry. Today I will present the thesis titled Fuchsat Classification of Ukrainian Use. The presentation will go as follows. We will start with motivation and the primary goal, then go through background, research goals and objectives, present an approach to solution, talk a few words about the data set, about the experimental setup, present the results, and wrap up with the conclusions. So for starters, machine learning in general and text classification in particular has one issue in that uh, the algorithms are typically data hungry, requiring large volumes of data to generalize well on previously unseen data. And at the same time, low data scenarios when large volumes of data are not obtainable are quite common in real life. And this problem has spurred an occurrence of a um, framework called Fuchsat Learning, and which aims at training efficient algorithms with limited training data. Large effort has been put into Fuchsat text classification in English, but not as much into other language, including Ukrainian. And therefore, we defined our first and primary goal as building a robust Fuchsat classifier for the Ukrainian language. Um, Most recent modern works on Fuchsat text classification rely on transformer-based pre-trained language models like BERT or GPT, and use prompts, which are texts written in natural language containing either explicit instructions or examples that guide the model's behavior. For instance, in a case of mask language models, close prompting is used. So a target word is masked with a mask token, and the model predicts a word in its place, which is then assigned one of the predefined classes. And in case of a large language model like GPT or Llama, um, in a setup called in-context learning, a model is presented with a prompt with several examples that have text and labels. And finally, it has a text with no label and is tasked to generate a correct label for it. Prompts may be quite tedious to create, and therefore quite a few alternatives have been suggested to these setups that either do not utilize prompts at all or try to automate their creation or somehow ease it. And it is important mention here that there's no single optimal strategy and definitive state of the art in Fuchsat text classification, because methods rely on different model architectures, use different number of examples per class. They also use different benchmarks and so forth. It is also worth noting that often large holdout sets are used for model or prompt or hyperparameter selection, which violates the assumption of true few-shot learning, where such large holdout or validation set is not accessible. And hardware demands are often not considered, which limits the applicability of the approaches in low resource scenarios, which is especially important given that pre-trained language models tend to be computationally heavy. As for the Ukrainian language, there are only so many works that we are aware of. One of them utilizes full shot, typically more traditional methods on a small data sets of word descriptions, and others use in-context learning with moderately sized large language models for several classification tasks. Given all that, we have defined the following research gaps, which are, it isn't clear which existing solutions, except for in-context learning, are adaptable and to which degree to the Ukrainian language. There's a lack of baselines for the Ukrainian, and applicability of methods in true few shot and low resource scenarios is under question. Therefore, our objectives are to review existing solutions for the English language and assess their adaptability to Ukrainian, suggest our own solution, as well as provide several diverse baselines, and compare time and computational complexity of the methods to assess their applicability in a low resource scenario. Our primary solution is based upon set fit, which is short for sentence transformer fine tuning. This is a method based upon sentence transformer architecture, which maps texts, typically sentences or paragraphs, to continuous dense vectors. And the set fit comprises of two parts. First, a model body, a sentence transformer model body is trained to efficiently encode text belonging to different class in the embedding space, and then the embeddings produced with a fine-tuned sentence transformer model body are used to train a model head, which is typically a logistic regression or a single layer neural network classifier. Um, our proposed modifications to the method involve self-training of multiple model generations, augmentations, and the usage of artificial holdout set for evaluation. Here is the schematic depiction of our proposed solution, which we simply call modified set fit. So we start with the training data, which is used to train a sentence transformer model body. After it is the data set is augmented with textual augmentations and encoded with the transformer model body. Then embedding augmentations are applied over it, and these texts are used to train the classifier neural network head. And the outputs and in the train classifier is used to predict pseudo labels for unlabeled examples, and the high confidence predictions of these unlabeled examples are used to train the next generation of the model in the same fashion. And we proceed with training model generations until two consecutive generations show either no improvement in accuracy or the accuracy declines. We also train two ablations. One does not use text, one does not use augmentations, which we call multi-generational set fit, and another does not train, and with another we do not train multiple generations. Our augmentation pipeline consists of several steps, namely its back translation from Ukrainian to English and back to Ukrainian, random word swap and deletion, TF-IDF replacement. Then the texts are embedded, and over embeddings mix up augmentation is applied, which proportionally mixes uh, text vectors and their respective labels. For the baselines, we chose, well, obviously vanilla set fit, ADAPET, which is a method based on masked language model and that utilizes prompts. Perfect, which also is based on masked language models like BERT, but does not use prompts. Then in context learning with Mistral 7B large language model, and in context learning with model fine tuning. For the dataset, we used UA News, which is a dataset of news from Ukrainian online media, where texts are broken into 5 categories: business, politics, sports, technology, and news, which is an umbrella category consisting of examples that do not fit into the rest. As you can see, the distribution of data here is skewed, which has implications on our work, which I will talk about shortly. As for the artificial holdout used for assessment of generational training, We use two large language models, namely Mistral 7B Instruct and GPT 3.5 Turbo, accessed with OpenAI API. And well, we fed them with prompts, with examples, and got the artificial data as a result. The data, the final artificial holdout data set contains about 700 examples. And as you can see, data, the distribution is also skewed. As for the experimental setup, for each method, we train two variants with 8 and 16 training and validation documents per class. As I mentioned before, we cannot base the model selection upon the full test set. And for that, we use artificial holdout set. And due to the skewed distribution of the data, apart from accuracy, which is the typical metric in papers on the subject, we also report macro F1 score and weighted F1 score. Here, you can see the experimental results in the table. So for setup with 8 examples per label, which is the left part of the table, set fit, multi-generational set fit shows the best results with accuracy and weighted F1 of 0.84 and macro F1 of 0.82. Set fit, modified set fit also improved upon vanilla set fit. And just augmented set fit shows about the same score as vanilla set fit. As for 16-shot classification, vanilla set fit has shown the best results. You may see that the scores for multi-generational set fit are the same as for the vanilla set fit. This is because based on the model evaluation, we have selected the first generation of models. So basically, these two are the same. And the perfect shows about the worst results, at least in 16-shot setting and in context learning, despite relying on by far the largest models among the ones tested, also has quite moderate performance. Here in the graphs, you may see the accuracy for multiple generations of set fit, of modified set fit, and multi-generational set fit with a different number of labels of text per label, with blue line representing the test data set accuracy and the orange line artificial holdout accuracy. So basically for all models except one, we stopped with the second generation, as consecutive third and fourth generation show the decline in the performance. And for set fit multi-generational with 16 examples per label, the decline in accuracy is displayed right away with the second generation. So we stopped with the first generation, like I talked before. And as you can also see, the pattern of artificial holdout accuracy follows test dataset rather closely. So we can say that our application of it as a criterion for evaluation of models and stopping of multi-generational training was a success. Here from the graph, you may see that multi-generational set fit for both 8 examples per label and 16 examples clearly overfits. So the training loss converges rather quickly, while the evaluation loss remains relatively well with relatively small changes over epochs, and what could be the cause for this? We hypothesized that high confidence predictions made from the unlabeled dataset were not informative enough to update the next model to bring new information to the next generation of classifier. And a possible way to see this could be to check the lexical diversity of corpora. The idea is that the lexical diversity of the corpora with added new high confidence predictions should be lower compared to the random samples drawn from the full training dataset. And as a test metric, we used Spearman's rank order correlation. This method was proposed by Kilgraph, who simply ranked the words into corpora by frequency and then computed this metric between the ranks. So the higher correlation score corresponds to lower diversity between two higher similarity, a higher score um, stands for higher similarity between two corpora. So as you can see from here, we ran experiments on with 10 trials on with random samples from full training data set. And we got an increase of 0.16 in the correlation score on average between consecutive corpora, while for pseudo-label predictions, we got on average plus 0.08, which did not allow us to say that lexical diversity is the cause here, or at least it is not indicative of the problem. But we assume that in the future work, the multi-generational training could benefit from advanced self-training techniques, which use some advanced, for instance, thresholding for selecting the data to add to the new training set. We also, for the measure of speed and computational complexity, measured the time for the model to inference time for the model to predict 1,000 examples on a with GPU acceleration, without GPU acceleration, and also contained floating point operations per token, which is kind of a common metric for computation complexity in such cases. And the lower the scores, the better. So as you can see, SetFit, both modified and vanilla, because our modifications do not affect the inference in any way, is by far the fastest method, and also the one with the lowest computational complexity, relying on lightweight sentence transformers. Um, here you can see that for inference on GPU and both without GPU, it by far surpasses other methods, while predictably in context learning lags far behind. For other methods, they are kind of in between. But so it is worth mentioning that SetFit is arguably the only method which is still viable for large-scale inference in production environment without a graphical processing unit. So its applicability, so it has the best applicability in a low resource setting. To summarize, It is, to the best of our knowledge, the first time that for Ukrainian, multiple methods based on for fuchsia text classification based on different pre-trained language model architectures were tested. We established a few shot state-of-the-art for UA news dataset with accuracy of 0.85, with best performance for 8 shot, shown by our solution multi-generational set fit, one of the ablations, and for 16 shot shown by the vanilla set fit. We evaluated inference speed and computational complexity with best results shown by vanilla slash modified set fit, and proved the viability of artificial holdout for the model evaluation. And yeah, which is important in the absence of a large holdout set not available under true few shot setting. And as for the future work, we believe that evaluation of more available methods and techniques should be done. There's still quite some room for that. For instance, possible directions could be automatic prompt search and generations, usage of more powerful large language models, because Mistral 7B is a moderately sized LLM, advanced self-training techniques, and other data augmentations. Obviously, more testing should be done on other data sets apart from UA News, and further assessment of synthetic data utility should be done to confidently say that it can be a replacement for the test data in scenarios when it is not available, but there's a need to assess the classifier and pick model or hyperparameter or prompt. This concludes my presentation. Thank you.
Thank you for a nice presentation. I have several consecutive questions. Now let us start with the data. We didn't see any examples of the documents you used in your experiments. I do wonder how much noisy these documents are.
Just a second. I have here a small example. So in terms of noise, I would say, well, based on rather superficial assessment, that the data set is not very noisy, but there are cases when a human, human annotator could attribute one text to one category or the other.
Okay. Could you please go back to your diagrams?
This or
No. And one step more, please. Yeah, okay. Um, yeah, diagrams in the next slide, please.
uh,
Next slide. Yeah.
yeah.
It could be easily observed here that the generations after the second are useless.
Yes.
In fact, are you sure about that? Have you ever tried to have more generations just to verify if there is a sort of anomaly later on in the process?
Uh, well, for multi-generational set fit, we tried more generations. For
How many?
8 examples, 5, just one more.
Okay, I'd really suggest you to go further to 10 to 15 to be just to make yourself sure that the picture is the same. But anyhow, uh, to have sort of a grounded hy- hypothesis about this phenomenon, Why the second is the last viable?
Um, well, once again, it is quite hard for me to pinpoint the exact reason. I assume that further examples predicted by the model are just not very informative for the training of the next ones. And as the next graph shows, it just kind of overfits without much use of the new data.
Yeah, that was the next question about the overfitting. I just hypothesized, looking at these diagrams, that the overfitting might be the result of excessive noise in the documents. This is why I asked you, was the dataset noisy or not?
Um, do you mean noisy in terms of text quality, for instance, or
In
for?
terms of regular word combinations, which do not help in terms of proper classification,
Uh, this could be a
like
possibility.
headers, footers, URIs, or something like that.
Okay. No, it is quite clean in this
Mm.
regard. So I'm assuming this is not a reason.
Okay. If you look at the table 2 slides ahead, no, no,
Before,
two
sorry,
slide, 2 slides
I'm sorry.
before. Yeah, sorry. Uh, mm, could you please reiterate what is the current state of the art performance for this task? Is it the SAT fit, basic, your baseline, or what? Or you have some other competitive solutions that demonstrate state of the art performance?
No, well, SetFit is not the state of the art, at least for the English language.
Mm.
And as I said before, there's no kind of definite state of the art because, as you can see, I've made a comparison table of various methods,
Ah,
and basically they all use different benchmarks and different number of examples and different models. So there's just no way to pinpoint a single state of the art.
Okay, thank you. This is it.
But by the way, you could fill this table. You could reproduce these methods on these data sets and give us more full results. Do you agree? You had this possibility.
Yes, I agree that uh, well, for many of these methods, there's no well way to reproduce it for the Ukrainian language because some additional computational linguistic resources are required, like
Okay.
WordNet or something like that. But for some, yes, it was dictated by just time constraints.
Okay. Anyway, can we have a live demo right now?
Um, well, I'm sorry, I have to open the code and go through everything.
No, 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 no. Live demo, like give a text and got the labels, got the answers to these categories. Categorize the text
Uh,
to
w-
get any text from internet and check how well this model work on real
well,
data.
I would need like 5 or so minutes of preparation for the to run the script.
But at least we can. Okay, so we'll think if we can allow this 5 minutes. Okay, super.
Okay, no problem.
The next question is what is about multi-label classification?
Um, uh, this is kind of an issue with many again of these methods, as for instance, perfect and ADAPET used for for the baselines do not allow for multi-label classification, while SetFit does. So it's kind of a non-standard task among the typical works in this on the subject.
But why have you not challenged yourself with this question?
Well, I find the task of this data set quite enough considering the amount of experiments I needed to run. So
Okay,
yes.
understand. And third question, can you please once again comment why in your appendix B, you showed on the slide, there is no answer for the category of second text?
Um,
So for me, it's pretty obvious that category can be selected from this question. Yes,
Here, right?
yes, second
So
one.
this is the example of in-context learning. So in blue here is the example provided to a model, and here is the final text. And this is just to show that the model has to predict the label here,
But have it
generate it.
okay, but have it predicted?
This is just a hypothetical example, but yet yes, it does predict.
Okay, thank you.
Yes.
I have, thank you, Evgeny, for presentation. I have a very short question on slide 28. When you have Spearman correlation coefficient, what is D? You sum over D, but yeah,
Yeah.
sum D square, but what is summation over?
Um,
So
so I mean, D is the ranks of the words. So
how many words? What words in? So what do you?
yeah, yes. So this method ranks the words into corpora by their frequency, and here the ranks of the like corresponding positions are summarized, and based on this, the correlation between these ranked lists of words is computed.
But you need you need two instances to compare ranks.
Yes,
But what is the second one?
I mean the rank list of words from one corpus and from another.
Okay.
Yes, yes.
Um, Thank you, Evgeny, for your presentation. Also have a couple of questions. So at the beginning, you mentioned that this task is poorly studied for Ukrainian. And what is the, I understand that there are multiple data sets and so on and so forth, but what is the state of the art result? What is the state of the art accuracy or of one score for example, English, and how close you get with Ukrainian?
Again, for English, it is hard to tell single state of the art due to plethora of data sets and setups. For Ukrainian, I don't have it here in the presentation, but basically it is some results for toxicity with Mistral 7B, which shows.
I'm asking about English, not Ukrainian.
Oh, okay. For English, this is just a. Oh, I'm sorry. For English, there's just too many data sets to say that, well, there's a single state of the art. For instance, for age in use, which is the closest to ours, the best results, as far as I can tell, are shown by iterational pattern exploit training here, and mixed text. No, I'm sorry. Here, the second slide. Yeah, that's correct.
And so what is the metric here?
This is all accuracy.
Accuracy. Okay. And in your case, what is your accuracy in Ukrainian?
Well, the best is 0.85.
Okay. Um, so I also was curious, could you please go back to the slide where you list the models or approaches you were trying? Um, okay, for example, Mistral 7B. So was it like one shot, or was it fine tuning, or
Yes, so we tested two setups. Mistral 7B was chosen from several other large language models with moderate sizes, others being Llama and I'm sorry, Gemma. And we used in-context learning with three examples per each class for demonstrations, like the text goes and then the label for the text is. And as another setup, we used in-context learning with fine tuning with with low rank adaptation, for which we used training and validation examples.
okay? And I'm also curious, what is kind of the level of understanding Ukrainian by Mistral? For example, can we? So, does it make sense to use Mistral to for Ukrainian language? Does this model understand Ukrainian at all? And
I would say it is pretty decent. Compared to other two models we tried, it is superior. And so, yes, it makes sense to use it. Also, it obviously hallucinates often because it's quite small.
because in my experience, I guess yesterday I tried it during one of the defenses, and it was like I asked Ukrainian questions, and it returns just garbage.
Mhm.
So that's why I'm asking. But okay, if in your case it works, and I'm also curious about slide 27. So this seems very odd to me, but did you observe the same trend for other trainings, or like why did you decide to show us this curves?
Um, well, the trend is kind of the same, but for instance, for the first generation of all set fit models, the evaluation loss decreases over the epochs, while here you can see that for fourth generation it rises. Well, so this is just to illustrate that here in the fourth generation, as an extreme case, there's a problem with the overfit.
Okay, got you. Thank you.
Just a quick question from me. Are you certain that this kind of setup for this kind of task is not language neutral?
It is obviously not language neutral,
I don't think so.
and it is limited by the languages supported by our underlying pretrained language model of choice, which is multilingual E5 small, and the same goes for the other models used in other methods.
How does the language information, how is language information used in the classification pipeline? So
Uh,
naively speaking, I to take the bag of words, I do build the similarity in the index. I build some vectors of these features. I feed it into the system, and I get a sort of classification out of it. It does not rely on any language.
well, in this case you speak of, it is indeed can be language agnostic if we do not use any additional resources, like, for instance, part of speech tagger. But as all our experiments rely on transformers, they are trained to encode texts in particular languages, and so they would not perform well on, I suppose,
But
Latin if it does not
but
support Latin.
you do not really look into the tokens-like sentences or multi-words, multi-token settings. You just operate with singular words, aren't you?
Um, I'm sorry.
You pick single words from the text. Why do you need this linguistic sugar over the bag of words?
Well, in the case of setfit, we
Mhm.
use embedding of the text as a whole, so it is mapped to a
Okay.
continuous vector.
Okay.
So we do not consider separate words.
Fair enough. Yeah. Thank you.
And please be prepared for the demo during the break.
All right.
Maybe one last quick question. So I'm just curious. I usually ask this question. So I would be curious to see failing examples and working examples. So for example, you achieved accuracy, say 85, and why is this limited by 85? What are the failing examples? And have you performed this type of analysis?
Yes. In short, there are, if you allow me for a second, there are confusion matrices here in the end of the presentation. And for set fit, like some trends could be observed. For instance, the sports category is very confident across different models, but then news and politics are often mislabeled because, well, they're quite close on the manual inspection. So uh, some news on, I don't know, crime could be in both categories.
This, yeah. So it's so I'm just it looks why didn't you put like Ukrainian labels? And I'm also curious news. So you are classifying news and you have like news in your category.
Yeah, as for Ukrainian language, I just suppose my presentation is in English, so I should be presenting categories in English. And then for the news category, like I said, it is in an umbrella category for everything that does not fit into the four others.
And very, very short question. In the two examples you showed us, what would be the classification label for the second one? Because it could fit both business and technology.
I'm sorry, can you repeat?
The two pieces of news you showed us on the other example, Appendix B.
Yeah,
Yeah, the second one, it's clearly multi-labeled.
well, the dataset considers it is technology, and typically news about like innovation and tech are in the technology category.
Well, actually.
Yeah, I think we are over time and we can move this to the break. Thank you, Yohani. Yes, we are moving on, and the next student will be Irina Pastukhova, and she will be presenting a thesis entitled Meaning Change Detection in Text, and she was advised by Andrei Lubonko.
Okay, today we are going to talk about detecting changes in the meaning of the textual data. As it has been already mentioned, this thesis was advised and authored by Andriy Lubonko. Oops, excuse me. Meaning change detection can be represented as a concrete NLP task called paraphrase identification. It is a task of determining whether two sentences express the same or very similar meaning despite potentially being formed from different set of words. In particular, it can be stated as a classification task, mapping two sentences into a 0 or 1 or into some score of their similarity. In our investigation, we consider this paraphrase identification task as a binary classification task. It is worth mentioning that sentences can be formed from a very different set of words but have the same meaning or vice versa. A common example is shown on the slide. All three sentences are formed from the same set of words. However, first and the second possess the same meaning, while the third one the opposite. Paraphrase identification task is important due to its intrinsic presence in any other, not any other, but in many other NLP tasks. For example, it is crucial for question answering, translation, text summarization, and simplification, because all these tasks involve comparing the meaning of input and output values. Also, it is paraphrase identification can be useful in such important task nowadays, like plagiarism detection, because it can help to determine the cases where the text are formed from different words and have different structures, but still possess the same meaning. Also, generating paraphrases can help in data augmentation. Generally, there are three main approaches to solution of this task. The first ones are based mostly on syntax, semantics, rule-based heuristics, and statistical methods, and usually they involve structural representation of data and then followed by some matching algorithms. Also, deep learning-based methods use neural networks and large data sets, and LLM-based is just prompting the models. State-of-the-art solutions mostly use BERT-like deep learning models like BERT, Roberta, or Ernie. Also, the state-of-the-art solutions provide good performance. Being deep learning models, they lack of interpretability and require significant computational resources. There is a tendency nowadays to use quite a theoretical mathematical methods of category theory in different spheres of life, engineering, and sciences, and this approach is called applied category theory. So recent advances in this area possibly allow to extend the list of solutions of paraphrase identification tasks with the ones that are better interpretable and possibly more intuitive. In other words, applied category theory allows to model the structure and semantics of natural language. The general idea of this approach is just to take the text and convert it to some diagrammatic representation, or by analogy with quantum theory, to text circuits. And possibly it is supposed that such representation of textual data can make applicable that these methods to be run on quantum computers. According to the most recent results in this direction, the text circuit represents its meaning, and also text having a similar text circuit representation should have similar meaning. This fact allows us to apply the theory to our task of paraphrase identification. And also, it is worth mentioning that there are already some frameworks that realize all that ideas and help in applying this method to the task. So the aim of the thesis is the following. First, we wanted to apply some BERT-like models to our task, also explore the abilities of LLM models, and investigate the quantum NLP methods which are based on that categorical ideas. For paraphrase identification, of course, dataset selection is crucial. All previously mentioned methods were used on two different paraphrase datasets. The first one is POS. POS is special in that sense that it was formed from the sentence pairs that are formed from quite similar set of words but have different meanings. And one more important point about the POS datasets is that the authors of that datasets state that if some model is trained on POS, then it performs very well on other datasets. So the second dataset is Quora question pairs. It is just datasets containing pairs of questions taken from the Quora site. And on the one hand, POS was formed based on the textual data from Quora. On the other hand, POS is more refined datasets, while the Quora question pairs can be considered as more natural and like less cultivated data. So this distinguishes between the considered datasets allowed us to reveal some interesting properties of the method that we used. First we applied the deep learning based approach, and here we chose the Roberta model. The reason for this, for choosing this model was the following. First of all, Roberta is the representative of the state of the art of deep learning models, and secondly, it is an improved version of BERT, and in the original paper that presents the POS dataset, there was the performance of BERT reported. So the initial idea was to compare Berta and Roberta and BERT on POS and to know if it indeed can outperform the BERT on this dataset. Also, we need to train and evaluate Roberta on POS on Quora question pair and make some cross-evaluation of the trained models. Why cross-evaluation is important? It's just in order to reconfirm or disprove the statement about the improving the model performance after training on POS dataset. As can be seen from the table, Roberta met the expectations and a bit outperformed the BERT on the POS dataset. Further experiments showed that despite the difficulty of POS datasets, Roberta was able to outperform it comparing to the experiments on Quora. Also, cross-evaluation of the pre-trained model in general proved that beneficial impact of POS datasets in enhancing the model's generalization abilities, stated by the authors of POS dataset. And also, we can see that pre-training on POS provided like much bigger accuracy on while evaluating on Quora question pairs, but the contrary case was not so successful. But in general, as we can see that the accuracy of cross-evaluation was still lower than the accuracy of evaluation by the directly trained model. So POS is like helpful, but it's not as perfect as can be expected. For the LLM approach, we use zero-shot prompting, relying on the model's ability to generalize from the pre-existing knowledge. In particular, we use two versions of GPT 3.5 Turbo and GPT-4. To debug and improve the prompts, we followed the recommendations from the official documentation presented by OpenAI. So we used several iterations of prompt engineering and tested our prompts on the sentence pairs that Roberta failed to classify. The final prompts are shown on the slide. The main point here is that these two prompts are quite different in their structure and complexity. The first one is very simple and basic, while the second adapts persona and have some extended description of the task. Initial prompting of the model, we made provided some like insights from it. In general, both versions of the model, GPT 3.5 Turbo and GPT-4, perform significantly better on quora question pairs. The initial and most intuitive conjecture here is that GPT in general can understand some more natural, less refined data better. Also on POS, we saw that GPT 3.5 Turbo is more like sensitive to prompts complications than GPT-4, which behaves almost constantly. And finally, model complexity is in some sense like inversely proportional to prompt complexity, because GPT-4 can infer from complex tasks from the minimal instructions, whereas GPT 3.5 Turbo requires some more explicit guidance. So we performed the final evaluation on the most like optimal prompt model combination, and it was the simplest prompt for quora question pairs and the like more refined and with more instructions for POS. And for consistency, we used the same model version GPT 3.5 Turbo on both datasets. The results show that still GPT understands better the simpler data in structure, because in general all the metrics are better for GPT 3.5 on quora question pairs. So the last considered approach was quantum NLP. Generally, this approach includes the following parts. First of all, we need to select some tool or framework that helps to realize all that ideas and text conversion from like conversion from textual data to some diagrammatic or circuit representations. And then after choosing that framework, we need like to convert text and then train models on that like data representation. So we chose Lambek. It has all that steps, and actually it has three model modifications. One is classical, one is hybrid, and pure quantum. Classical, it consists, no, like not consists, but it involves representation of text data into text tensors and applying classical computations. Quantum represents text in text circuits and requires quantum computations, and hybrid is some combination of both of those. So our initial plan was to select subsets of POS and quora question pair. What is worth mentioning here that the text conversion to any quantum-like representation takes computational resources and time. So that's why we selected a subsets of quora question pairs and POS. The next step was in our initial plan to use the latest version of the framework to convert the textual data to circuits, and also train and evaluate all the model modifications. So the final data sets that we used is presented here, and also on the slides in the bottom we can see the simplest diagrammatic representation of the sentence. However, the selected framework was not like mature enough to use it for our initial plan. At first, the diagrams that it generated had incompatible formats, and what is worse, the most interesting hybrid and quantum model modification failed to run due to some intrinsic framework errors, which we were not able to fix. So we adjusted a bit our plan by switching to using some older but stable version framework, and ran experiments only on the classical model modification. So in general, we used more categorical approach, but not quite quantum. And unfortunately, the model failed to learn enough from the data to be able to predict something. At POS, we can see that it fails to predict at all, but on Quora we have much better result, but it's still worse, significantly worse than for previous methods like deep learning and LLM. So all the above results can be presented as such an inequality. In particular, our results show that even with the rapid development of LLMs, the more traditional language models such as Roberta is still the better choice, at least for our concrete task and data sets. And at least in the settings we considered, the QNLP approach is not yet ready for practical use and falls short in terms of accuracy compared to LLM and Roberta-based models. Thank you for your attention.
Thank you for the presentation. Anyone would like to start? Let's start from Rostislav.
Thank you, Irene, for presentation. I have a question regarding this difference between the two data sets, pose and Quora question pairs. Can it be the case that the QQP consists of longer sentences, longer questions? They are not refined, they are just inputs from the natural speakers, so natural users, real users, and therefore too verbose, too wordy, and this adds more context to the LLM.
Actually, it's a contrary case because in POS the usual case is where the sentence looks more like a paragraph, not a sentence, but in Quora it's quite short questions. So it's like that.
Thank you, Irina. Can you get back to the slide 21? And actually, before asking the question on the slide 21, the previous one. So what was the main motivation to play with this quantum mechanics, QNLP, whatever?
Because it's new and interesting approach. Actually, this was the most challenging and exciting part of all that investigation, I would say. So that was the motivation. And it sounds just cool, QNLP, you know.
Great. Yeah, I mean, that's a great, the major motivation for the researcher is curiosity. So kudos. But then again, so you used, because I'm not familiar with this totally, and is there some prepared frameworks that exist, so you just feed the data and run the program, on you need to create your own, I don't know, code to run those models?
Actually, there are some prepared frameworks which provide us with models types, I would say, and actually the tools for converting data to any representation. Basically, there are frameworks which should be used in some ways, but for example, training and data, I would say preparation, it is on our side.
And you somehow, it's impossible just to put data in classical terms. I mean, like those texts, you need to somehow prepare it for this QNLP frameworks. Is it correct?
Yeah. It's not that you take some text and then put it. You take text, you convert them to the diagrams that were shown. Then the diagrams even are converted further to like some other converters, and then the data is ready to be like inputted into the model. Because the diagram is the most like I don't know. The most obvious and the most pretty way of showing the data, I would say.
So back to this slide, what is your understanding? Why is such great difference between those two data sets, specifically in precision and F1 score results?
I suppose that's because of complexity of POS, to be honest, because I saw the examples of using that framework, that particular framework, and that model modification to some very like simple sentences, and the accuracy was very high. So I suppose that here it is due to the differences in complexities of that data sets.
I take a look at your thesis and investigate examples from POS. It's obviously, even for human reader, it's not that obvious from the first point of view to understand what's the difference between two texts. And could it be that the problem is this arises for the POS, that when you convert from text data to those diagrams, that actually the diagrams could be, so we have two different texts with the same, actually pretty the same set of word tokens,
Mhm.
but with different meanings because of the, those semantics. And then we converge it to the diagrams. And could it be the chance that the diagrams for those two different texts would be actually the same? And from this moment, the Q and OP will fail.
Um, I suppose, yeah. Actually, I investigated those diagrams, and uh, they are quite complex, and it is even hard to
To debug.
yeah, to debug and to see any difference between that diagrams representation. Are they similar, or they have some small I don't know, distinguishes?
Yes, it would be interesting to investigate further. Thank you.
Do you have ideas how to improve these bad numbers, these small numbers? What we can do, not just waiting while QNLP become more mature and so on,
Uh,
but what we can do now.
Actually, that classical any of that models has some customized architecture. We use some that was like proposed by the authors of the framework, and it is quite simple. So I suppose the first step could be just to make more like difficult and complex model architecture and try to use it on POS. I suppose that's the first.
How many trials you did to get this number? So only once, or you tried 1, 2, 3 times and kind of summarize these results? Because of, as I understand the randomness, you could get different results for different trainings and so on.
So basically, no. It is the best result obtained
It's
by
the best. Okay.
by the training the model.
So even you get worse during the
Yeah,
training.
yeah, during the training.
Thank you.
Yeah, also have a couple of questions. I'm curious about your comparison with Bert and Roberta, if you can maybe open that slide.
Mhm.
So you provide just as accuracy, but I'm curious about, you know, training. So how many epochs you did? What was the setup?
Oh, actually, we just used our setup that we used for training on the whole data sets and everything, and we just compared the best accuracy with those that was reported by the post authors. So actually, I don't have that information. I have to present.
Okay, I see. I see. So you didn't compare the training setup, you compare just the final accuracy.
Yeah, there's just the best results of theirs and ours.
Yeah, also you reported training one model on one data set, then cross-evaluating it on another data set. Have you tried like merging those two data sets and then training the model on two, but keeping the some holdout test data set just to see what can be the upper bound of the performance if we train on a large enough data set?
Oh, actually, we didn't try it, but that's a good point.
Also, about your experiments with large language models, can you open that slide? So given that GPT was trained or on enormous amount of data, it can be the case that both of this data set fall into its uh, training data set. So maybe these models can memorize and so like my question is, have you maybe tried some real examples that were not present in the internet but maybe written by you just to verify it works?
Actually, I tried it, but they were quite simpler than those provided by POS and the question pair. And suppose the correct answers could be because of that, I don't know, simplicity of my examples.
And also about those QNLP results, you reported the matrix, but if I recall it correctly, you mentioned that you didn't convert whole data set, right? So it was just a sample of the data set. So what was the sample size? What was the like? Okay. Um, and what is the fraction of the whole data set? Is it like 10%?
Oh no, it's
5%?
the whole POS, I suppose, has nearly 40,000, but quarter question pairs is some kind of
Okay, so it's very small sample.
very small
Then
sample.
maybe when we convert to the whole data set, like, do you think that it can results can change or
Actually, I'm not sure, but maybe in some. I tried smaller sets and those presented on the slide, and actually it wasn't observed any improvement. So I'm not sure. Maybe when we use really large sample sizes, then it could provide some improvement.
Mhm. And final question from me is about failing cases. So have you maybe performed an analysis of what cases are failing to what I don't know, false positives, false negatives, and
Um,
um, in this case?
to be honest, not really, because it wasn't like uh, our aim, I suppose. But it is an interesting point to compare failure cases of all the methods and
Yeah, because it can be, for example, that the models performs well on relatively short uh, paragraphs and performs worse on longer, and so then you can work on different strategies to improve your results.
yeah.
Yeah,
Thank you.
got you. Are there any questions? No? Then thank you, Irena.
Thank you.
25 minutes break. That's fantastic.